We can analyze the running time of merge sort using that recursion tree that we had. So again, in this tree, we have that each node represents a recursive call. So we can figure out how many recursive calls we have to make, how many levels of recursive calls we need, and then how much time we spend individually within that recursive call, not counting any other recursive calls that node has to make. So let's see, how much time do we have to spend at each level? Well, for merging these two smaller sequences into this larger sequence, we know that the merge takes time, which is linear with respect to how many items there are. So the amount of time we spend at this node, not counting the recursive overhead, is linear, is n. The amount of time that we spend at this node, not counting those recursive calls that we have to make, is also linear, but this time we have half of the number of elements we had before. And here we have half of the number of elements we had before. If we add up how much time we spend at this level, though, this is n. And similarly, at the below levels, now we have even smaller lists. The cost to merge these two sorted lists into one sorted list is linear with respect to how many items we have here. We have n over 4 items here, and n over 4 here, n over 4 here, n over 4 here. So we have 4 sequences, each of size n over 4. So we have a total of n elements if we count up the total amount of non-recursive overhead for every recursive call at this level, not counting those additional recursive calls they have to make. So the amount of time that we spend at each level is linear. So now we just have to figure out how many levels we have. And this is based off of, I promised we would continue to use this again, but you can think of this as figuring out when do we reach the base case of our recursive calls. This is when we have a small enough size input. So this happens when we have 0 or 1 elements. So we start with n elements, and then we repeatedly divide by 2, until we're left with just 1 item. So how many times we have to repeatedly divide by 2, beginning with n until we're left with 1? This is log n. You can also think of this as how many times we have to, beginning at 1, repeatedly double until we reach n. So our total running time for merge sort is how much time we spend at each level, which is n, times how many levels we have, which is log n. So merge sort runs in big O n log n time. So let's see how this compares to the other sorting algorithms that you've seen so far. But when we're comparing sorting algorithms, there's a few things we want to take into consideration. One is the runtime. Definitely we want it to be efficient, to have the smallest time complexity, meaning it runs the fastest. But we also care about how much space it's using. So we saw a few algorithms that were in place, meaning that they only required a constant amount of additional space. It's only using exactly the data structure that it was given. It's not using any additional data structure. It only keeps track of this constant amount of memory that it's using is usually to keep track of pointers or indices, and then some swap operations occur. The third thing we care about specifically when comparing sorting algorithms is the stability. So we say that a sorting algorithm is stable if it preserves the original relative ordering of elements with equal value. So you might be thinking, why would you want to preserve the original ordering if we're sorting? We want to change the order. But the idea of a stable sort is that for those items that have the same value, equal value, meaning it doesn't matter where with respect to each other we put them, as long as we put everything less than it before it and everything greater than it after it. For those items that have the same value, a stable sort will preserve whatever order we had them in originally. So for example, if we had this sequence, and let's say these two b's have the same value, this is just, I have them here to indicate this is the first b and this is the second b in the sequence that we were given. So this isn't a sorted sequence, but if we had a stable sort, we could guarantee that after we sort all of these items, since this was the first b that we encountered and this was the second b we encountered, then in a stable sort, we would keep that our first b came before our second b. If we didn't have a stable sort, then it could be that they're placed in a different order. So still we have a total order of items, but that first B we had encountered was capital B, and that's not the first B in this unstable sort. Right? So if we have, again here we've got, let's say, oops, here's our B1, let me put it this way, B1, A, C, B2, no matter how we sort these, as long as we put them in some kind of an order, we'll have A comes before B comes before C. A stable sort will ensure that this first B1 will continue to be the first B in our resulting order. So we would have A, B1, then B2, and then C. So we keep that this first B1 we had before continues to be first within all of the B's that we have. Whereas an unstable sort would put them in some other order. At least we couldn't guarantee that that happens. So why would we care about a stable sort? Because these have the same value. So what does it matter if we put one before the other or not? Well, it becomes important when we have complex objects that have multiple attributes associated with them, which realistically this is what we would have in a larger program rather than just a list of numbers. So maybe these are people objects, right? And they have a first name and a last name and a phone number and social security number and all of these other things. And if we want to sort repeatedly by a few different attributes, we would need a stable sort in order to preserve the order of our first sort. So for example, in the phone book, you have people that are sorted based on their last name, and then for all of the Smiths on page 70, you've got all of those guys sorted based on their first name. So if you wanted something like that, then you would have to use a stable sort. So we would first sort by first name. So we've got all the Abigails before the Johns. And then after we do that sort, so we preserve the first name ordering, but our next sort would be by last name. That way, for all of those people that have the same last name, we preserve the original order, which means for those values, for those same last name values, we have them sorted by first name. Okay. So how do the previous sorting algorithms that we've seen compare with respect to time, space, and stability? Well, selection sort and insertion sort we know are not as efficient. They run in quadratic time. But we saw for them implementations which were in place. Unfortunately, selection sort is not stable. For example, let's say, so here's our selection sort, an example as to why it's not stable. If we had just the sequence B1, C, B2, and A, and we're using the in-place implementation of selection sort. So we'll start by selecting whichever one is the minimum, and we're going to replace it with this first item. So we're going to grow our sorted sequence on the left. So A is the minimum, we're going to replace it with the first one. So we've got here now A, C, B2, and now we've already changed that B1 comes after B2. And if we continue our selection sort again, we'll select whichever one is minimum, which in this case of all of these is B2 or B1. We'll pick whichever the first minimum we find is, and we'll swap it with the next one that comes in. Here's our already sorted sequence. So this is the first item we haven't sorted yet. So now we've got A, B2, C, B1, and then again, now here's our sorted sequence. We take the minimum item, we swap it with the next one. We're left with an unstable order. So this is not a stable sort. Selection sort is not stable. Insertion sort, we can implement and make it stable. And the reason for that is every time we take our next item, we're kind of growing our list from the left there and inserting them in order. So let's go back to, here's our insertion sort. We take that same list, B1, C, B2, and A, our first step will be to insert B into a sorted list. B1, just because it's the first one. Okay, cool. That just by itself is already sorted. Then we insert C into this sorted list. So we're going to compare it with just the item that comes before it. It's larger than this item, so we're going to keep it where it is. So this is now our sorted sequence, B1 and C together. Now we take B2, we insert it into our already sorted sequence. So we're going to compare it against C. It's smaller than C, so we're going to put it before there. We're going to compare it to B1. It's not smaller than B1, so we're just going to leave it there. So we've got B1, B2, C, and A. So we preserve this order that B1 came first, and it continues to be first among all of the Bs. So insertion sort is a stable sort. And we can implement this in place. But both of these are not very efficient comparatively. Now heap sort, we did see how we can implement this in place using a vector implementation, but then we have that this is not a stable sorting algorithm. And the reason for this is because we end up swapping with our last node whenever we call remove min, and then we end up changing the original order of items. Merge sort, this isn't an in-place algorithm what we talked about, but this is stable. And the reason for this is we can always prioritize when we merge equal elements. We can prioritize the left side before equal elements on the right side. But this is not in place because we have another sequence that we use in order to handle the merge operation. But this does give us sequential data access. So this is good if we're sorting data that's so large it can't fit into main memory and instead has to reside in slower external memory. Then we can use this to read in chunks of data small enough to fit in the main memory, sort them, and then write them out to a temp file. This is also convenient to make parallel for the same reason. So we can kind of cut our sequence up into more manageable sized chunks and sort them in parallel. Okay, so with sorting algorithms, you'll notice I've got three things here, whether it's in place or not, if it's stable or not, and then the runtime. Usually with sorting algorithms, we have kind of that trifecta of how much space it uses, how long it takes, how much time it takes, and also whether or not it's stable. And in general, you can pick two. So what we talked about in the previous implementations, certainly you can implement some of those algorithms. The ones that said that they weren't in place, we could figure out a way to implement them in place, or if they weren't stable, we could maybe in a more complicated way figure out how to make it stable. But usually when you try to gain one of these things, you end up losing out on another. So maybe you can make something stable, but then it's not as efficient. If you have any questions, post on Piazza, reach out, let me know.